Hello, I'm Hugh Mannfield and welcome to my science channel. Now today I'm going to be doing something a little bit different. I'm going to be doing a deeper dive into someone else's video. Now if you don't know who these guys are, and how could you not? Anyway, it's Derek from Veritasium and Destin from Smarter Every Day. Now they do some of the best science content on the net. But this one particular video I had a problem with, and it is the Veritasium video about measuring the one-way speed of light. So in the video, Derek sets up the situation and then he brings in Destin and he asks Destin about his supersonic baseball measuring technique. Now if you haven't seen the supersonic baseball videos, they're great. You should watch them. But wait until I've finished with this one. Anyway, Destin measured as the ball passed between 2 points of a known distance apart. Then he took the amount of time it took, frame by frame with his high-speed camera, for the ball to make that distance, and that got him the speed. And then he realizes that Derek is up to something probably that has to do with relativity. And this is the case. Derek brings up the paper by Albert Einstein that includes the stipulation that in order to synchronize a clock, we must allow that the time that it takes light to travel from A to B is equal to the time that it takes to travel from B to A. That is, the light travels at the same speed in both directions. And this is called Einstein's stipulation, according to Derek. And it is kind of the basis of the rest of the video. So Derek explains how this works in a space-time diagram. And I don't really like working with space-time diagrams very much because it's kind of like working with nitroglycerin. If you don't do it exactly right, it can blow up in your face. Now, here we have a typical space-time diagram, time passing along the vertical line, the vertical axis, and space represented across the horizontal axis. Now, in this case, we have the Earth, and in Derek's example, he used Mars. And we see a signal traveling at the speed of light along the 45 to Mars and then back to Earth. And it takes 20 minutes. Now, according to the math of a space-time diagram, that same trip could occur at half the speed of light, taking 20 minutes to get to Mars, and then an instantaneous transmission back to Earth. So according to the math, these two solutions are entirely possible. And as Derek points out, from the perspective of someone on Earth or someone on Mars, we couldn't be able to tell the difference. Now there is one problem with this, and that is on a space-time diagram, something moving on a vertical line is something that is at rest, passing only through time. So this would mean that Mars is at rest with respect to the Earth. And that's not really true, but it's a simplification. And in this case, in order to make his point, Derek may have sensationalized or oversimplified just a bit. And I know that's kind of a shocking thing to say about a YouTuber, that they would sensationalize their videos. Anyway, so how does this actually work? Now, Derek mentioned in his video that physicists had worked out complete systems for this non-uniform speed of light. So what we would have would be a case where in one direction, light travels at an infinite velocity, and in the other direction, it travels at c over 2, c being the known speed of light, or the average uniform speed of light that it would take. And so for Derek's example, that speed must change by some sort of function with direction. Now, I don't know what that function is, and I'm not going to try and figure it out because this isn't my proposal. So if Derek wants to explain that more in another video, that's up to him. The thing is, any round trip would have to be composed of light passing along a path that forms a uniform line, whereas the pairs of velocities would match such that the round trip would average to the speed of light. And that brings us to the only known location, is that at the perpendicular, light would have to travel at c. So let's see how this would actually work. Now, if we modify Destin's supersonic baseball setup, and we put instead of the stakes, we have a beam splitter and a mirror of a known distance apart, and then downrange with equal length legs, we set up our receiver where we have a very accurate clock, and we send out a pulse of laser light, and it is split. One travels directly to the receiver, the other travels across the known distance, and then along a line of equal length to the receiver. And this should allow us to measure the one-way speed of light, because these two legs will cancel out. So let's see what this means when we apply Derrick's non-uniform speed of light with direction proposal. You might say that if we just look at the components, we can work out that we've got some round trips of light going on. But with the non-uniform speed of light, especially with the infinite speed of light, it brings up some serious questions. If the speed of light is infinite on this component, then what does this component have to be in order to get light to propagate from this beam splitter to the receiver? In fact, you might argue that if the speed of light is infinite in one direction, then in that direction, light can only propagate in that direction. You can't get propagation of light, which would mean you would have some blind spots. You would not be able to see the mirror from the receiver. So that's one problem I see with Derrick's infinite speed of light. And you can solve that by saying, okay, well, maybe it's not totally infinite. Maybe it's just very, very big, but still finite. So let's look at some of the cases. In this case, we have the infinite speed of light along this direction, which means the signal reflects from the beam splitter and the mirror at the same instant, and then they travel on different paths to arrive at the receiver. Now, along this path, the light will be traveling slower than the speed of light. Some component that's going to be between c over 2 and c, and along this path it's going to be traveling faster than the speed of light, some component that's between c and infinity. And you might say, well, how do we know what that's going to give us? Well, there's actually some symmetries involved here, that if you take this component, reflect it around, you get a line that's parallel, which means we have compatible pairs of velocities, and then if we slide that line down, we see we've got a round trip of compatible velocities, and that is going to give us a solution where the delay between the two signals is going to equal the amount of time it takes for light to cross between these 2 points at c. So the result, we'll measure the speed of light as being c. And if we take some of the other cases, we keep turning the direction where light moves at infinite velocity to a different angle, we end up basically getting the same result no matter which direction we point it. So in each case, pointing the direction of infinite light speed along either the vertical or horizontal axis will give us the same result. The time it takes light to pass between these two mirrors is the speed of light. So you think, well, maybe Derrick's onto something here. Maybe we can't tell exactly what the speed of light is through some sort of measurement. In that case, where the math gives us something ambiguous, this isn't the only time this has happened in physics. And what happens then is that you look toward observations and you try to see, okay, are there observations that will rule out some of these mathematical cases, or give us one mathematical case that matches observations? And that's what we should do now. In 1905, when Einstein wrote his paper, there were a lot of things that we know now that he didn't know. Like, we know about the evolution of galaxies. Back in 1905, they thought the universe was the Milky Way galaxy. They didn't even know for another 20 years or more whether any galaxies existed outside the Milky Way. We know about changes over time in the expansion rate of the universe. Well, in 1905, they didn't even know about the expanding universe. We know about black holes. Now, black holes at the time were probably just a speculation. Now, there is one case where Einstein could have known, and that is in Maxwell's equations, especially the Heaviside configurations from 1880. And Maxwell's original equations dated earlier than that. So Einstein certainly had the opportunity to know about this information. Another thing we've seen, which has to do with measuring the speed of light, is the gravitational lensing of distant galaxies. And this is something that Einstein wouldn't predict until many years later. And we also know about the cosmic microwave background, something again that Einstein didn't know about in 1905. So let's take a look through these cases and see if we can say something about whether light speed can vary with direction or not, whether there's observational evidence that would either support or contradict it. So in the evolution of galaxies, we would look out into the distance and we see the nearby galaxies at a certain state of evolution. And as we look through space, we see farther back in time and we see galaxies in earlier and earlier states of evolution. Now, as Derek pointed out in his video, if light speed was infinite in a certain direction, if you looked in that direction, you would see everything in, quote, real time, or as it is now in some cosmic sense. And in that case, in that direction, you would look out and you would see fully evolved galaxies as far as you can see. Whereas as you start looking in other directions off axis, you would see galaxies begin to show their evolution history as you look further and further back in time. So the evolution of galaxies supports the constant one-way speed of light as being c, is uniform with direction. So let's look at the expanding universe. Now, if we looked out in the direction where light was coming at us at an infinite velocity, and we would see the instantaneous expansion rate. We wouldn't see a change over time. We would see galaxies into the distance, presumably redshifted by a constant amount. Whereas as we look in other directions, we see either an acceleration or a slowing of expansion as we go back closer to the Big Bang. So what this would give us is a non-uniform expansion. As we try to draw a map like this one of the expanding universe, it would be lopsided. In one direction, it would expand at a certain rate, but in other directions, there would be a history of expansion. So you'd have a straight line on one side and curved on the other. So once again, the fact that we see a universe that expands uniformly regardless of direction, that argues in favor of the one-way speed of light being c, no matter which direction it's traveling. It argues against Derek's proposal or the space-time diagram result of variations in the speed of light with direction. Now let's talk about black holes for a minute. Black holes are objects where nothing can escape even if it's moving at the speed of light. But what happens if the speed of light changes with direction? If the speed of light is infinite in one direction, well then in that direction it seems like there couldn't be a black hole. If it's infinite velocity, it's going to be able to escape no matter how strong the gravity is. So what you would end up with is a black hole that has a bright side and then presumably maybe even a darker side on the other side. Anyway, it would be lopsided, and something orbiting the black hole would follow a non-circular path I mean, the black hole would be oblong. It would be open on one side and closed on the other. And what we've made of observations of black holes, this just isn't the case. They seem to be pretty round, which argues against the one-way speed of light varying with direction. And that brings us to Maxwell's equations, something Einstein could have known about. What Maxwell discovered as he looked through his equations is that these two properties of spacetime, the electric permittivity and the magnetic permeability, their product is equal to 1 over the speed of light squared. And these quantities can be measured in electrostatic fields and magnetic fields. And what it would mean if light traveled at different speeds in different directions is that these properties of spacetime would also have to vary with direction. And we know that's not the case because when we measure electrostatic fields, the permittivity is uniform regardless of the direction it's measured from the electric charge. And when we measure magnetic fields between the north and south poles, they distribute evenly. There's not a large side and a small side. So Maxwell's equations pretty well confirm that the speed of light must be uniform in all directions, that space-time is isotropic. Something that didn't happen in Einstein's day or wasn't known is the gravitational lensing of galaxies. Now, there are cases where we can look out into the universe and we can see multiple images of the same galaxy being lensed around another galaxy that's in the foreground. And we found this in a lot of different places, and they all seem to work the same way regardless which direction we're pointing the telescopes where they're found in the sky. And what happens is that due to the lensing, the path is bent along a different line, so that those different lines have slightly different lengths, and the difference in the lengths can be several light years. When we see a supernova in one of the images, it may be a few years before we see that same supernova in another one of the lensed galaxy images. In fact, given the geometry, these can be predicted from either 3 to 10 years, and this has been done. And that prediction is based on what? It's based on the one-way speed of light being c. And when they make that prediction, you can wait, and in 10 years, or 3 years in this case, the supernovas were seen in the other images as predicted. So this is a confirmation of the one-way speed of light being c. And you can't argue that there's some sort of round trip going on here. Light came from the distant galaxy to the Earth, a one-way trip. And that brings us to the cosmic microwave background. As Derek pointed out in his video, if you look in one direction where the light is coming at you at an infinite velocity, you see everything in real time. Every photon is new light. There will be no old light coming from that direction. Well, the cosmic microwave background is said to be the oldest light there is. So, in the direction where light is coming at you at infinite velocity, you would not see the cosmic microwave background. But the one thing about the CMB is that it is very uniform, which really nails down that Derek's proposal of non-uniform speed of light is just not true. We see very uniform cosmic microwave background, which means that the light is arriving the same amount of travel time no matter which direction it's coming from. What Derek has basically discovered is just a quirk with space-time diagrams. With space-time diagrams, you have to take a look at them and say, okay, is it really telling me something that makes sense? Sure, the math works. It doesn't break the math. You know, Derek claimed that it doesn't break physics for either of these cases to happen. Well, it doesn't break the math. Physics is something different, and physics is what we learn based on observations. And observations tell us that this is the actual case that's going on. Light is traveling at c no matter which direction it travels. And that brings me to another story. And this is a story worthy of a Veritasium video. What does Jupiter's moon Io and these three fellows, what do they have in common? Well, in 1612, Galileo had been observing the moons of Jupiter, and he saw that they made regular cycles, predictable cycles, as an orbit would be. And he proposed that they use the moon Io, which is always eclipsed as it passes behind into the shadow of Jupiter, to be able to establish longitude. Now, this was back when the hunt for longitude was on, and there was a prize offered by Spain for someone who could come up with a solution. And Galileo's solution actually worked, at least from land-based telescopes. You could travel and make observations of when Io was eclipsed. You could compare that to the observation taken on the prime meridian, and based on your time of day, which you established by local noon, you could find out the difference between your longitude and the prime meridian. This could be done through correspondence after the events, and you could nail down the position quite accurately. But it was not practical for ships at sea, and that was the nature of the prize. Galileo did not receive the award. People continued to use Galileo's method for land-based observations, and a Dutch astronomer, Ole Roemer, was tasked with tabulating the almanacs and observing and predicting the eclipses of Io. And as he collected data, he began to notice something. As Jupiter passed from opposition, where it would be opposite the Sun to the Earth, that would be the closest approach to Earth in its orbit, and then as the Earth moved around and Jupiter followed its orbit, as Jupiter approached conjunction with the Sun, the eclipses of Io were slightly delayed. And he couldn't figure out why this was happening, because at the time, light was thought to move basically instantaneously. Going through all the data, he finally arrived at the conclusion that the speed of light must have some finite, although large, value. And through his calculations, he arrived that over the diameter of Earth's orbit, 2 AU, this amounted to roughly 20 minutes, which was not a very good estimation of the speed of light. But it was the first time someone had actually put a number on it, and it kind of got us into the ballpark. But it took a while for Ole's theory to catch on. As people continued to use Galileo's method, they kept finding these discrepancies. And eventually, by 1809, there was enough data that had been collected that Jean-Baptiste Joseph Delambre, I hope I got that right, was able to calculate the speed of light more accurately based on these measurements. Now, one thing about Delambre is he headed one of the expeditions to measure the length of the prime meridian across Europe and establish the length of the meter. And this was when the SI units, the scientific units of measure, were being established. And this also gave him a better handle on being able to make the calculations. For Ole, he had to convert AUs into some other old archaic length measurement system, which wasn't necessarily very accurate. But Delambre was able to calculate that over 1 AU, it would take light about 8 minutes and 20 seconds to travel that distance. And our current number for that is 8 minutes and 16 seconds. So he did a great job of narrowing in on the speed of light. And in fact, having this value enabled the design and construction of measurement devices for use here on the Earth. And on the Earth, it's impractical to use the one-way speed of light because of the distances involved and the time spans involved. You just simply couldn't measure it. So they would use long distance or multi-reflections to increase the length of the path. But you can't argue that light coming from Jupiter's moon Io to a telescope on Earth is involved in some sort of round trip. Now, it came from the Sun, but it reflected off Io, and from there came to the Earth. That's a one-way trip. And this is an amazing story of how one-way speed of light was known by 1809. That's almost 100 years before Einstein wrote his paper and made his stipulation about the one-way speed of light, which means that Einstein was really introducing his own silliness over something that he could have known. And if he had written his paper properly, he would have cited the known examples of why we can reliably believe that light travels at the speed of light, c, no matter which direction it's moving. So as Derek closes out his video, he talks about, then what's the point in even talking about it? And the point is to make creative and thoughtful videos that inspire thought. And Derek, you inspired a lot of thought. Thank you very much for something to think about in the middle of the night when I should be sleeping. And the only way to get over that, I tried leaving comments, but I decided instead to make this video. My conclusion is that by modifying Destin's baseball measurement setup to use the beam splitter and the mirror, we can actually measure the one-way speed of light here on the Earth or in some other setup. It's not practical, but in theory, it could be done. Now, there are a couple of things I would like to say to Derek and Destin in this. And first of all, Derek, this is a good video, but among all your videos, it's probably a stinker, in my opinion. It's not as good as the rest because it tends to imply something that isn't true, that we can't rely on the fact that the speed of light is the same no matter which direction it travels. And Destin, you basically had this gut reaction in the video. Isn't light at the same speed in every direction? I think you said something like that. And my advice to you, Destin, is stick to your guns. You had the gut feelings right. And don't let Derek bully you just because he's a physicist. Engineers are just as smart as physicists, and in some ways, more practical ways, they're even smarter. They make things work. So, in conclusion, I would like to say that, Derek, you owe us a clarification on this video. For all of you viewers of my channel, if you like more of these deeper dives into different subjects, just let me know in the comments and leave a like and subscribe. And until next time, I'm Hugh Mannfield.